Hello Internet! Welcome to the third and the last episode on our three-part mini-series on Word2Vec. Last time we trained our model. Remember, this was our Word2Vec model. We trained for 20 epochs, and now we're gonna validate if the training made sense. Of course, you can have here for the positive negative and negative positives graph. But let's do the typical thing that we always do, and this is the embedding lookup and analysis. So what you're interested in is to get the weights of the hidden layer. So there's a very simple function where you have your vocabulary, and I'm sure you're familiar with the embedding projector, where you download your vectors in a TSV file, in a tab-separated file, and your metadata in your tab-separated file. And then you just open the embedding projector. Let's do this for a second. If you are not familiar with it, this is a beautiful 3D visualization. I think it's up and running for almost close to 10 years, and it's a very, very well-known visualization tool. You then say, okay, what I want to load my own tensors, and then you just upload your TSV file of vectors and your TSV file of metadata here. You say, choose the file you download from your local notebook or from your cloud account. And then it is calculated for you. And as you can see here, you have either the very simple PCA, the principal component analysis, the classical t-SNE, or if you're really into topology and you really want to have some very, very strong performance, clustering and classification, you use UMAP. That is also standard here. And as you can see here on this predefined example that Google provides for you with the Word2Vec in 10Ks, of course, you see that UMAP is running here and it's trying to optimize it for 400 epoch, and it's done very fast because we're here in the cloud. And this is, for example, your 3D distribution. And if you're searching for some words, let's say science, on this data set, you choose science. You have here the cosine similarity, all the different words that are close to science. And if you reduce it a little bit, you can see here where some cluster is happening. But of course, in our example, what I'm going to do it a little bit different. But of course, I want to get my weights, because this is why we did the Word2Vec model, to get particular weights. And then I also create my TSV files. Let's do this very fast. It should be a short video. As you can see, our shape is very easily. We have a vocabulary size of 32Ks. So these are our words, and each and every word is encoded in a numerical vector representation in a 128-dimensional vector space. This is it. For every word, we have a vector in a high-dimensional vector space, and now we are able, let's say, we have to define the cosine similarity. Sorry. You can use something from NumPy, or just to show how it is done, I did it here simply in Python. And you can, of course, use NP, no problem at all. You say, just for classification, my hidden nodes are 128, my vocabulary size is 32K. And then I just define a word. This is my target word. And I hope there is some sentences with this word in my training data set. Otherwise, I have to find some other words. So let's hope we are lucky. And let's execute this. And what it does, as you can see here on this code, it calculates the cosine similarity from this particular words to all the other 32,000 words in this 128-dimensional vector space. And this takes some time, normally up to 20 seconds. And what I told it to do is show me the 25 words that you think are semantically closest to my first words, to the Higgs boson, And you know, here we are in high energy physics, elementary particles, quantum field theory, gravitational renormalization theories, and we have hadron, mesons, strange leptons, decay boson, proton, lepton, the Yukawa matrix. So this, the gluon, the neutrino, decaying, the colliders, this is absolutely where you would say, yeah, this looks similar. This is really a clustering that around Higgs we have here based on our training data set of our 129K sentences. The system was able to identify semantically close, semantically similar words, how in the structure that it appears in the sentences in our training data set. And if we say, I don't know, something trivial like, what is a trivial? Science. And you might ask, okay, if we have science, what are the semantically closest word to science given our particular training data set of European research or R&D, research and technological development projects? Let's see if around the cluster focusing on science around this particular word, there are other words that make sense to us as humans. And here we are, disciplinary, multidisciplinary, science and actions, inquiry-based, nanophotonics, curiosity-driven science, advisors, industry, academia, tribology, it's material science, space-related, stepping stone. Yeah, this looks nice, but you see that here sometimes that industry slash or space academia, sometimes it puts together two words, inquiry-based, science, action. Maybe these are also two words that we have to do. We have to further improve our tuning algorithm where we define a customization of the KERAS preprocessing TensorFlow input data pipeline. My goodness, those are words. So there's a lot of to be done, but this looks not bad. Let's choose something else. What about cancer? Sure, there's some EU research going on the topic of cancer. Maybe there are quite a lot of sentences about medical research. I don't know, I haven't checked. This is just out in the blue. Let's see if we find some result where you would say, yes, this makes sense. Our algorithm, our word model is working. Come on. Well, yeah, no, it doesn't really look metastasized. Yeah, nanoparticle based. Okay, so we have maybe to do a little bit further fine-tuning and cleaning up in our input data set, because I think that some space-related splitting is not happening here in the right way. We have to go back, investigate in the original data set, and find out if something happens in the configuration of the vectors. But no problem at all. This system, this is just for demonstration. The system is working. Let's do some very simple. What is simple? University. I think this is a word where we all have some personal impressions on. Let's see what the system comes up with. But remember, we are running here under free COLAB. We just had used 10 gigabytes of RAM. So of course, and the training happened in I think 5 minutes. So of course, this is just a demonstration of the ability of the system, but I think it is quite nice. So we have University, Autonoma, Maastricht, the Maastricht University, Technische University München, yes. Limerick is a university, Orsay, yes. Washington, Twente, yes, in the Netherlands. Okay, so interesting. And you see here the value for the cosine similarity. If you have a model that's really fitting very well, and if you have trained it for hours, I can tell you that here the cosine value comes up to close to 0.8, 0.9. And if you see here, of course, if you check for a multiple set of words, You can see here that the overall performance sometimes is not strong enough. Maybe you have to train your model a little bit better. You have to prepare your input data set a little bit better. But this is it. This is the third video, the last video on Word2Vec. If you want to take care of all the advances in TensorFlow 2.7 and all the particular KERAS layer options that you have, it is gorgeous. Again, remind you, check out the original documentation of KERAS here, working with preprocessing layers. This is where we took care of our advantages. And of course, check out, as we have here, our TensorFlow original tutorials. They are beautiful tutorials. If you look at the TensorFlow documentation, you have it for beginners, you have the KERAS basics, then you have it for expert customization, distributed training, multiple GPU, TPUs. You also have some very nice YouTube videos. So look at this, make yourself familiar. I hope with this video you got an idea that it is not so complicated to apply current KERAS methodologies, current TensorFlow 2.7 methodologies and functionalities. It is really worth experimenting. You can accelerate your model quite a lot of. It is quite fast with 15 seconds for our epoch training, the time period. This is great. And I hope you get interested, you try out for yourself. And I wish you all the best, and I see you in the next video.